All right. So it's 11:30. So let's look at the answers and solutions to the questions in the worksheet. So the first question is more of conceptual, trying to explain heat loss by conduction, convection, and radiation. So we have here double Rex rats. Double Rex rats are hairless. They don't have hairs compared to their normal counterparts. And the question asks us, using convection, conduction, and radiation, discuss the disadvantages that the double Rex rats have compared to their normal rats in regards to temperature control. And of course, the main difference is that double Rex rats don't have fur, and so it's the bare skin that's exposed to the environment. So in terms of convection, heat loss by convection, which rat do you think will lose more heat by convection, the double Rex rats or the normal rats? Yeah, the bald rats. The double Rex rats who don't have fur should lose more heat by convection, right? So the heat loss by convection is higher. Convection, again, is the bulk movement of air. So so you have, imagine air moving across the skin of the rat, and as air particles or air molecules brush across the skin, they carry with them heat. They carry away heat from the skin of the rat. So if you have the normal rat with fur, the fur sort of traps air, traps air, and the trapped air insulates the skin and protects it from the circulating air. So heat loss by convection will be higher in the bald rats because bulk movement of air is easier. And as air moves across the bare skin, the air carries away heat. In terms of conduction, it's a similar thing. It's just the conduction between the skin and the air particles that are sort of stationary around, or even conduction between the skin and the surface, the floor, for example. So if you don't have fur, conduction will be higher. Heat loss by conduction will also be higher. There's no thick fur. So the layer fur sort of gives you this thickness that prevents the heat transfer from the fur to the surface. And that's why without the fur that serves as a barrier, heat loss by conduction will be higher because the skin will be in direct contact to the cold surface, for example. Heat loss by radiation will also be higher. So heat loss by radiation will also be higher when you have bald skin, just bare skin. So the emission by radiation can occur easily from the skin. Emissivity of the skin is also higher compared to the emissivity of fur. So maybe that's the main reason, because emissivity of skin is higher without the fur. So those are some explanations for the disadvantages of the bare skin compared to when you have fur covering the skin. All right. Okay, let's go now to the next question, which is a numerical one. So an adult rat has a surface area of around 0.04 meters squared. So surface area is 0.04 meters squared. It has an internal body temperature of 39 degrees Celsius. So that's the temperature of the rat or the body of the rat, 39 degrees Celsius. The emissivity of the skin, we take that to be equal to 1. We want to calculate the rate of thermal heat loss via radiation on a 23 degrees Celsius day. So that means you have a rat, it's exposed to its environment. The environment has a temperature of 23 degrees Celsius. So a difference in temperature between the rat and the environment will allow heat transfer by radiation. You'll see there's some useful information that was provided. So the sigma constant is given and also the equation for heat lost by radiation. But take note that this equation is just the radiation loss by the rat itself without considering the environment. So if you want to consider the environment, which in this case you should, because you have the rat is in an environment with a different temperature, 23 degrees Celsius environment, then you should consider the effect of the environment on the heat loss as well. Right, so you should use the equation, so E sigma A T rat to the 4 minus T environment to the 4. So you should use the equation which incorporates the temperature of the environment. We want to find the rate. So rate, that means Q divided by T. Okay? And so this time should go in the denominator on the left side instead of on the right side. Cool. All right. Before you can use the equation, you need to convert your temperatures to Kelvin. So add 273 to each of your temperatures. You should have 296 Kelvin for the environment and 312 Kelvin for the rat. Okay. Then you can substitute everything to the equation. E is 1. Sigma 5.67 times 10 to the negative 8 times the temperature of the rat in Kelvin, 312 raised to the power of 4 minus 296 raised to the power of 4. Yeah. Okay, I'll do the calculation step by step because in the past, some students had problems with so 312 this one, if you do this calculation, 312 to the power of 4, that's essentially 312 times 312 times 312 times 312, right? You should get 9.4, I'll just round it here, times 10 to the 9, something like that. If you do that here, 296 raised to the power of 4, 7.68 times 10 to 9. Yeah, I'm just double checking. times the area. We're missing the area. Did we consider the area? Times 0.04. Right? Okay, so are you happy with that temperature raised to the power of 4? If you're using a scientific calculator, you'd want to look for the symbol that says x to the y. So your x will be, for example, 312, and what you put in the y is 4. So 312, and then hit the x to the y button in your calculator, and then hit 4, and that will raise 312 to the exponent 4. But in the end, you should get a rate of 4.08 watts. Okay. Right. Okay, are we happy to move on to the next question? I just want to make sure, because calculating the temperature raised to the power of 4 is probably the trickiest one. Yep, good. Okay, no problems. Cool. So the next question is also heat transfer by radiation. Skin temperature for the horse, so T horse is equal to 33 degrees Celsius. The horse has an emissivity of 0.7 for the skin, and the area is 6 square meters. Okay. Calculate the net rate of heat loss via radiation in a day when the air has a temperature of 14 degrees Celsius. So the air is 14 degrees Celsius. So again, you have the horse in its environment, and the horse and the environment has different temperatures. Make sure to convert your temperatures to Kelvin. It's really important that you do that for radiation questions. So 33 plus 273 gives you 306 Kelvin. 273 plus 14 gives you 287 Kelvin. Okay, and then heat transfer rate, again, it's rate. So that's Q divided by time, and it's by radiation. So you have E sigma times A times temperature of the horse raised to the power 4 minus temperature of the air, the environment, raised to the power of 4. Yeah. Yeah, so that's the equation there. Okay, emissivity is 0.7 times the Boltzmann constant, 5.67 times 10 to the minus 8 times the area is 6 times the temperature. So temperature of the horse, 306 raised to the power 4 minus temperature of the air, 287 raised to the power of 4. Okay. Okay, and hopefully by now you've figured out in your calculator how to do the exponent of 4, and you should get a rate of heat transfer of 472 watts. Right. Okay, the next question is related to the previous question. If if this was the only heat transfer mechanism present, meaning the radiation, the heat loss by radiation that you've calculated in question A, if that is the only heat transfer mechanism present, calculate the change in body temperature of a 450 kilogram horse whose specific heat is given here, and you want to calculate the change in body temperature if the heat loss occurs over 1 hour. Okay, so we have now here a different scenario. You have the horse that's losing this much heat, 472 watts of heat is lost because of radiation. Now, because the horse loses heat, its temperature will change. And it's this change in temperature that we want to calculate if it's been 1 hour, if the horse is losing heat over a period of 1 hour. Okay, so right, so change in body temperature that comes into Q equals MC delta T, right? Okay, whenever it's related to the change in body temperature, it's Q equals MC delta T, because delta T here is the change in temperature, which is what we want to find. So rearrange this. So isolate delta T. Delta T is multiplied to M and C. So we divide both sides by M times C, and we have delta T is equal to Q divided by M times C. Right, so what is M? That's the mass of the object whose temperature changes. So M is the mass of the horse, 450 kilogram mass of horse. And C, that's the specific heat capacity of the object whose temperature changes, which is the horse. And it's given as 3,470 joules per kilogram per degree Celsius. Okay. Right. So in essence, to solve delta T, we already have the mass and the specific heat C. We're given that. We then need to figure out what is Q. So Q is the amount of heat lost by radiation in 3,600 seconds or 1 hour. Right. So the problem says the horse loses heat over a period of 1 hour, and we want to figure out the change in body temperature because of the heat loss during that 1 hour. So for us to find delta T, we have to figure out the amount of heat lost by radiation in 1 hour. Okay, in the previous question, we already solved that heat is lost, 472 joules of heat is lost every second. So 472, of course, watts. Watts, of course, means 472 joules per second. Okay, that means every second, 472 joules of heat is lost. So from question A, 472 joules of heat is lost every second. Right. And I need more space, so let me create more space. Okay, I guess that's the space I have. Right, so from question A, we've seen that 472 joules of heat is lost every second. So in 1 hour or in 3,600 seconds, the amount of heat lost. So in 3,600 seconds, the amount of heat lost will be 472 times 3,600 seconds, right? Right? Because, yeah, 472 watts means 472 joules of heat is lost every second. So in 1 hour or in 3,600 seconds, there should be 472 times 3,600 seconds of heat that is lost over that 1 hour. And if you do the multiplication here, you'll have 1699 200 joules that is lost in 3,600 seconds or 1 hour. Okay, once you have the total amount of heat lost in 1 hour, you can now calculate the change in temperature. So the heat lost in 1 hour, 1699 200 divided by the mass, 450 times the specific heat, 3470, gives you a heat loss of about 1 degree Celsius. So let me just 1699 200 divided by 3470. Yeah. You'll have 1.1 degrees Celsius, or that's also 1.1 Kelvin. Delta T, change in temperature, that's why Celsius and Kelvin would be the same. All right. Okay, I guess you'll be seeing this sort of question quite a lot when you're given the rates and you want to find the actual amount of heat. Just remember that the rate is joules per second. And so to find the total amount of heat, it should be the rate times the time interval. So over 1 hour, that's 3,600 seconds that you need to multiply to the rate of heat being transferred. Okay, so the second to the last question, I think, yeah. So to keep the horse warmer, the owner puts a wool fiber blanket on the horse. It's again a conceptual question. Discuss how putting a wool blanket minimizes heat loss. If you think about it, the wool blanket is sort of a barrier. And of course, if you have there a barrier, you reduce heat loss by almost everything. So the wool blanket introduces a barrier. And wool has low conductivity. Yeah, we said during our lecture, wool is a good insulator, and so it has low thermal conductivity. The lower the thermal conductivity, the more difficult it is to transfer heat by conduction. So wool is insulating. You also decrease, having the barrier will decrease heat loss by convection. Yeah, because you have the wool, the blanket serving as the barrier, preventing the air molecules from carrying away heat from the surface of the skin. The wool blanket will also affect heat loss by radiation. The wool blanket will have a lower emissivity compared to the skin. So wool blanket will change the emissivity, and therefore the amount of heat lost by radiation. Yeah. Okay. All right. And the last question, calculate the rate of heat loss through the wool blanket. Okay, so rate Q over T through the wool blanket if the blanket 6 millimeters thick and covers an area 4 meters squared. Okay, so some keywords here will give you a clue as to the mechanism of heat transfer. So first there you have through the wool blanket. That means heat needs to transfer through, it needs to go through the wool blanket, and then you have there a thickness of 6 millimeters. So if you're thinking about the different heat transfer mechanisms, the only type of heat transfer that involves some thickness is heat transfer by conduction, right? Because in conduction, heat will have to go through a certain thickness for it to transfer from one object, for heat to transfer from one object to another. So yeah, heat transfer. So rate means Q over T, and we have the equation for the conduction. Thermal conductivity K times the area times the difference in temperature divided by the thickness through which heat is transferred. Okay. So we have all the information. So K, thermal conductivity of wool, is given. The area is also given. So the area is equal to 4 meters squared. The difference in temperature, okay, we've seen that in question A. So you have, yeah, in the introduction to the question, you have the temperature of the horse is equal to 33 degrees Celsius, and temperature of the air is equal to 14 degrees Celsius. And so delta T is equal to the difference in temperature, 33 minus 14. Is that 19 degrees Celsius or 19 Kelvin? So it's a difference in temperature, so Celsius and Kelvin would be the same. And the thickness, of course, you're given 6 millimeters. 6 millimeters, the prefix milli means 10 to the minus 3. So that's 6 times 10 to the minus 3 meters. Okay. Right, so you have everything. Thermal conductivity is 0.07 times the area is 6 times the difference in temperature is 19, and the thickness is 6 times 10 to the minus 3. The area for, oh yeah, wait, there's a mistake here. So it's not 6, it's 4. The area is 4. Yeah, the area is 4 meters squared, not 6. Okay, that will give you a rate of 887